Hello everyone, we are very happy to introduce you our team Chorrobot, our concept Chorrobot, which stands for Framework to Commission Challenging Dual Arm Operations Using Reactive Road Control. We are from the University of Leuven and we are also members from Flanders Make. So our main motivation is to move from traditional robotics that are typically deployed in large-size industries, in which there are high automation costs associated with programming time, the expertise required for programming, the use of calibrated fixtures, and the fences that are placed around the robots to separate robots from humans. So we want to go to more advanced dual-arm applications in adjunct manufacturing, in which Chorrobot aims at offering intuitive task commissioning of, for example, challenging operations that can handle flexible objects as inserting O-rings into pistons. Also the possibility of having two robot arms in the same workspace and handling collision avoidance. And to further exploit the dexterity of Chorrobot having 14 degrees of freedom to augment the workspace. So in this way we can handle fixtureless and non-rigid work pieces and in a human collaborative application. So the main key technologies that use artificial intelligence of our concepts are the possibility of teaching position, orientation, forces, torques, and the coordination between the two arms using our state-of-the-art method trajectory parameterized probabilistic principal component analysis. And on top of that, we can also enable the specification of other aspects of the task, such as, for example, the automatic resolution of constraints, such as, for example, the collision avoidance. And all of these can be intuitively commissioned using our graphical user interface, in which you can commission the sequence of action with its parameters, and it can be intuitively combined or tightly combined in our constraint-based reactive controller ETASL. So for the level of integration, we place Chorrobot at the very end of the TRL level, such that we are already working with workpieces that you can find in factories and in applications that are already very industrial relevant. And then our main customers are the robot manufacturers such as KUKA, that we want that offer the possibility of exploit completely their platforms for deploying challenging operations. And also system integrators such as FRS, which are already deploying challenging operations such as inspection in the factory of Audi. Other system integrators that can be, we are also targeting, are already using teaching devices to play and to record and play back motion, for example, in free space and in simple contact tasks. Additionally, we want to offer the possibility for manufacturing companies that they can deploy their own applications and they can further refine the applications. So for the economic impact and the competitive advantage, Chorrobot offers the higher productivity, increasing the economic impact, that is lower automation cost, meaning that there will be less commissioning time. So for example, for one application, we asked several system integrators, and they told us that they will spend around 20 days for commissioning one application. So we want to them offering the possibility to commission it from 1 or 3 days, depending. And take into account that the robot programmer can cost around 800 euros per day. We offer also less calibrated fixtures, so the design and development of these fixtures are between 1,000 and 2,000 depending on for the application. And the possibility of having higher flexibility and reliability, meaning less stops in the production line. Also, Chorrobots offer easier commissioning, enhancing the competitive advantage. So it will lower the barrier of industrial automation, so there won't be need of like very highly skilled robots, and offer an easier access for developing countries and SMEs. So take into account that the UN is already recommending developing countries to embrace automation. So now I want to let you with the challenging task that we prepared for you.
It is very difficult to program tasks that require two hands by using traditional robot paradigms. For this reason, we use artificial intelligence in order to teach Chorrobot how to learn to perform a challenging task by the use of user demonstrations. So in this first application example, you can see how an operator teaches the system how to install an O-ring, a flexible O-ring, into a piston. You can see that through the use of our easy-to-use tools, the system not only tracks position and orientation, but also all the interaction forces necessary to successfully execute the task. So after the operator demonstrates not only one but five different positions along the workspace, different demonstrations by switching the positions of the piston and also from the picking base. Then it is very important to simulate first the task and see that the knowledge was well transferred. So for this reason, we use the Microsoft HoloLens 2 to visualize in simulation in an augmented reality scenario the application. So you can see that it is very useful in order to check, for example, for potential collisions with the environment. Also that the reachability of all the work pieces is fine, and also that all the knowledge was well transferred from the operator that is expert in inserting the O-ring but not expert in robotics to the system. So after we simulate, we then can proceed to execute the task. So I will do that by the use of our easy-to-use graphical user interface that can be run in any mobile device or any device that has a browser. So I will initialize the task and then move the sequence. So you can see that the first thing that Chorrobot does is use our off-the-shelf vision system to detect both objects, so the piston and the O-ring base. And it is an off-the-shelf vision system that is very easy to program and to teach new work pieces as well. So after Chorrobot detects both of our work pieces, then he proceeds to execute the task, which uses the learned model from the human demonstrations. So as you can see, Chorrobot first picks up the O-ring, which is a flexible element, and then it proceeds to insert it. So programming this task with traditional robot paradigms would be very challenging because it not involves just point-to-point motions, but also all the positions and orientations, and everything is quite complex, and all the coordination between the hands is also learned. So you can see that Chorrobot also learns stable contact points, so it knows that it should arrive to the piston and then follow the groove to reliably execute the task and complete the task. So you can also see that Chorrobot uses the learned forces that were transferred from the human operator, all the interaction forces, to make this successful task. So now we will proceed to explain you the next task, but first I will command Chorrobot to reconfigure itself with the necessary tools. Wait, sorry. Yeah. I will initialize then. And I will run the sequence.
So now I'm going to show you the second application, which is to assemble solenoids for industrial pump. So when the application is initialized, the system will detect the location of the workpieces with the Pika 3D vision camera. So as you can see, the parts are not fixed on the table. And as soon as the locations are determined, we can then commission the robots. So you can see the robots are moving in parallel. This is also another aspect of AI in Chorrobot, is that our framework allows to automatically resolve conflicting tasks or constraints, such as here, the two arms need to occupy the same space. But you can see that they are avoiding collision. This is made possible because our framework allows to specify priority levels, different priority levels with the different robots. And these priority levels can be automatically adapted during execution time. This improves the flexibility of our framework because you can imagine that programmers can just specify a sequence of independent tasks for each robot, and then later on, as the number of robots are increased, they can simply compose this sequence in parallel without changing the structure of the sequence. This method is applicable regardless of the number of robots. So for example, if we need to add additional robot to increase the throughput, this can be done without much of programming. This also avoids the need to program high-level coordination, such as task planning, and will reduce the overall commissioning cost. The safety aspect of Chorrobot is taken care mainly in the sunrise controller, where programmers can specify limits such as maximum velocities or forces. But in addition to that, our framework also allows programmers to further refine the safety. For example, here, the safety is to avoid collision, but also other aspects of safety, such as avoiding collision with the table or restricting the workspace of the robot, can be easily imposed. So the insertion of the solenoids are performed with force-based insertion skills. This increases the robustness because the location of the holes, as you can see, are not so certain, but thanks to the force feedback, we can insert the solenoids quite reliably. So after the insertions are finished, the two robots are going back to their initial positions. And before we continue with the third task, I'm going to change the tool. Sorry for the delay. So now we're gonna.
Okay, can you stop it, please? Yeah. Just again, because it. Wait. This to go.
No?
Yeah, it's running now.
Okay. Okay. Okay, now I will give the floor to my colleague to explain to you the final task.
Okay, so let me press here. Okay, so our third task consists, sorry. Okay, so our third task consists of the inspection of an unknown 3D contour from a workpiece. So I will load the sequence again in the graphical user interface so you can see the third application. I will run the robots and move the sequence. Yes. So this type of tasks are useful when you want, for example, to, like the robot, to inspect a layer or the thickness of a painting layer in a workpiece, or for example checking for manufacturing tolerances of the workpiece, or even the surface finish of the contour or of the float surface of the workpiece. So now as you saw, we again use the 3D vision system to detect where is the workpiece. So again, we don't need the fixtures, and the robot will go to that position and grab it. So since we don't have previous information of the contour in this application near the model of it, the robot will use the contact information between the tool and the workpiece to adapt its orientation along the inspection. Also, as you can see, the left robot will start rotating or moving the workpiece in order to augment the workspace space of the left arm, of the right arm, since the 3D shape is complex, so we need to expand the workspace. So this is actually running an implementation of the task frame formalism, where the user can specify intuitively in which orientations or in which directions of the frame he wants to maintain a desired, or he wants the robot to maintain a desired constant linear velocity or angular velocity, while in which other directions he wants the robot to keep a certain force. So now that you already saw 3 applications that shows the flexibility of our framework, you may be wondering how can an operator can program this type of tasks from scratch. So for that, I want you to take a look a bit closer into our graphical user interface. Our graphical user interface consists of different applications of different actions that the robot can do, and the user can start composing those actions in order to create the sequence. So we have, for example, normal PTP motions, where the user can specify the parameters, such as the position and orientation that he wants of a certain frame of the robot to achieve. And also we have more complex blocks. For example, if we add a move learn model, that was the one that you saw in the first application, he can specify which learn model he wants the robot to execute, each arm, and also he can, if there is a, okay, maybe the focus a little bit, yes. So he can specify the position and orientation of the part if there is a fixture, but if not, then he can tell the system to use the position from the camera or to use the orientation from the camera, or both. In addition to that, the operator can specify if he wants to run the sequence that he is programming in simulation to check it that the robot is going to execute and to move as expected. This simulation can be viewed in the monitor or in augmented reality with the HoloLens, as you already saw in the first application also. Finally, he can initialize again the robot in the real robot, and then move the sequence and that's our graphical user interface. So now I will give again the word to my colleague for some final words. Thank you.
So as you saw, we were able to deploy successfully 3 challenging operations that are very innovative in the industry and also academically. We prepare an extra one, so an additional one that is out of fun and that also like summarize all the possibilities that Chorrobot has. So for that, I will just start again Chorrobot. So then it's about taking bottles from this crate of 6 beers. And it's important also to mention that we are leveraging 3D printing, so you can see that the tools are designed for get extra reliability in the tasks. So here also we change the fingers for the gripper, and that enables us to have like more reliability when they are performing the task. Now it goes to graph 1. So also something that you might be noticing is that Chorrobot is also mounted in a mobile platform, so the Flex Fellow of KUKA. So we want to offer the possibility for the factories to take Chorrobot to install them in different workstations, take little time for commissioning, and deploy Chorrobot in the different workstations. You could see how Chorrobot is very gentle, putting the Stella in the table, how he can coordinate the motion of the 2 arms. And this part is a motion that is transferred, or like a model that is transferred from also human demonstrations, where the human is teaching how to approach the opener to get into contact with the bottle and successfully open the bottle. It's important that our system also take into account velocity constraints, so there are not the high jerks that you exert when you open the bottle, but it's like taking into account this and then successfully performing it a safe way. So I would say thank you to Chorrobot, and more thank you to you for seeing our presentation, and we will be very happy to answer all your questions.